component we are to analyze is part of Will and Merlin's senior project, a 3 degree of freedom wrist exoskeleton. The image on the left shows a specific component selected for analysis, while the image on the right shows the full assembled mechanism. The goal of our project is to analyze and improve the design of the cover plate. The part supports the motor responsible for flexion and extension, so it needs to be strong but also lightweight. We used ANSYS to simulate stress, deformation, and optimize the design by adjusting the geometry while staying within the limits. Our objectives were to optimize geometry of key sections to reduce material usage, evaluate the equivalent von Mises stress to ensure design stays below material's allowable stress, and measure total deformation to confirm the structure remains stable under load.
We have 4 design parameters. First of all, we control the thickness of the circular base since we want to determine the volume and the mass of the solid. Secondly, we use the width of the circular base and the width of the 2 sections to control the solid mass and volume so that we can get a possible von Mises maximum stress. Next, I will talk about our design parameters. Now, I'm going to talk about our design constraints for our project. First of all, we are going to use material called PETG-CF, which has a tensile strength of 57 megapascals and a safety factor of 1.5. Additionally, we want to find the maximum displacement with the 2 sections from the circular base. Furthermore, we have 3 boundary conditions in our design. First, we make a circular base to be a fixed support. Second, we have 2 forces on both sections. One of the 2 sections has a force of 11.4 newtons. The other section has a force of 6.6 newtons.
For the meshing process, we used the meshing strategy with varying element sizes that tailored to different regions of the wrist exoskeleton cover plate. Our main objective was to achieve a mesh that could accurately capture stress gradients, particularly in high stress regions. We applied a finer mesh in areas with high stress concentrations, mainly around the motor housing holes and at the interface between the circular base and the left extending section. Coarser mesh elements were used in larger, low-stress areas. The image on the left shows the cover plate before applying a finer mesh to the left extended section, while the image on the right shows the model after the finer mesh was added. The mesh uses a total of 12,027 nodes and 6,056 elements. In our simulation, we noticed stress singularities in the region where the motor mounts to the cover plate. These appeared as extremely high stress values that don't realistically reflect the actual behavior of the component. The singularity happens right where the motor and the cover plate connect, which makes sense because that's also where most of the weight from the motor is applied. On the right side of the cover plate, we didn't see any singularities in our results. That is because there is no motor or significant load applied on that side without a heavy component like the motor adding weight. The stresses in the area are much lower and more evenly distributed. To check for convergence in our analysis, we ran 2 versions of the same simulation. Both were focused on equivalent von Mises stress. One used average stress results and the other used unaveraged. By comparing the 2, we found that the overall stress patterns were similar and the maximum stress values didn't change drastically. This told us the model was stable and our mesh was fine enough and the results had converged. Our simulation results also showed a maximum deformation of 1.1835 e to the negative 4 millimeters, which is extremely small. This means that under the applied loading conditions, the cover plate barely moves. Since the displacement is minimal, we can be confident that the part will hold its shape and not interfere with the motion of the device. We also checked the structural error, which came out to be 2.1554 e to the negative 6 millijoules. That value is very low, meaning the simulation is accurate and the mesh was good enough to give us reliable results. So overall, the analysis shows that the design is both strong and precise under the expected loading conditions.
The sensitivity setup consists mainly of the parameters and constraints chosen for the analysis. In our case, there are 8 parameters, with 2 being related to the desired objective output, the mass, as seen in the left image. Our input parameters were the 2 sections extending from the base, the outer diameter of the base, and the base thickness. The output were the mass, bone misses, and deformation. Moreover, the right image showcases the design points created by the ANSYS software. The same values created for the optimization were used to generate the sensitivity graph. In total, ANSYS generated 38 design points. Sensitivity results. The top image summarizes all the parameter values of the part created in Design Modeler. Graphing the 4 input parameters versus the von Mises stress gives nonlinear functions. All of them have a form of a parabolic function. As an example, the bottom image illustrates the base thickness graph behavior. The rest of the graph behavior are the following. Top is the outer diameter behavior, bottom left is section 2 with a screw hole, and bottom right is section 1 with the motor housing. As it can be observed, the one with a relative constant increase is section 1 with the motor housing because it has the largest force supply. Design optimization. The top image on the right showcases the input values for the optimization. There are 3 values we want to minimize, and there are 2 constraints. The upper bounds were chosen to be less than or equal to the maximum values from the initial FEA analysis. The values produce results when they are closer to the maximum initial value, which is used to identify the 3 possible candidates. Additionally, the table on the left summarizes the input values and has a graphical representation of the iterations. Column C, done after the optimization. Optimization results. After multiple tries, we were able to find the 3 possible optimization candidates. Unfortunately, due to the motor housing, section 1 was increased instead of being decreased. Out of the 3 parameters we aimed to minimize, only 2 could be achieved due to the part's constraints and geometry. Nonetheless, the base parameters were minimized enough to have an impact on the object's mass. Candidate chosen. At the end, we decided to go with the second candidate generated by ANSYS. It was the one with the lowest mass and minimized more parameter points than the other 2. The optimized version minimizes the outer diameter of the base, the screw section, the base thickness, and reduces mass by 18%. Factors impacting results. Some restrictions that may have affected our ability to generate a better optimization were the housing of the motor and the holes in the base. Both of these were fixed, which limits the number of iterations in section 1. Similarly, the holes in the base limit the reduction of the outer diameter.
Here are the references used. Thank you for watching.